and we know the definition of a sensor. We looked at potentiometers. We looked at, talked a little bit about analog to digital converter. You know, we just glanced through that, but we kind of understand that now, right? Okay. Like I said, when I get time, I'll hook up one of the little 1100s over there and bring a potentiometer into it. And we did absolute encoders. We did gray code, right? What's gray code? Not binary, but it's a high-speed counting code, right? Increment encoders, quadrature encoders, are we okay?
Okay. You said the increment encoder needs to know the position.
Well, the increment encoder don't know the position. That's the problem. All it does is sends it. So what we have to do with an incremental encoder is we have to establish what we call an origin. Where are we counting from? Now, once we've established an origin, so basically they just clear out the counters and they say, okay, this is 0. And then from then on, every pulse we got would mean a certain motion depending on the transfer function between the encoder and what's after actually moving, right? You understand? So like, 100 pulses might equal to an inch, right? Well, 100, that we would directly say 100 counts would equal to an inch, right? You understand? Because these are going to have to be counted. But what's nice about this is they have no fixed limit. They have no fixed range on the encoder themselves. All they do is spin and give pulses, right? You understand? So they're not limited to the number of revolutions. They don't roll over. Well, the only thing that we're limited is what the counters that we're putting these things into, right? That makes sense? So the counters that these things go into limits it. So how many bits are available coming out of that counter? We talked about the absolute encoders on a robot. They call them absolute encoders because from the controller point of view, they think it's an absolute encoder. When actually it's an incremental encoder, but the counters are part of the encoder. We looked at the differential voltage, the LVDT. This guy here outputs an AC voltage. The amplitude indicates the position, and the phase indicates the direction. Right? Make sense? These things look like shock absorbers. I think I tried to stick some pictures in here. So they look like what? They look like shock absorbers. They're very, very rugged. They're very, very reliable, but these guys are definitely going to have to be interpreted with some type of electronic circuit. It's just a basic LED circuit. It gives us direction, right? It gives us count. So a resolver is a type of transformer used to measure position. Operates kind of like a LVDT. LVDT is linear, right? You understand that? Okay. So it's going to have what we call a linear actuators will have what we refer to as a stroke. You don't know what a stroke is? This is the maximum distance that it can send. So if I can look at these guys right here. So if this is 12 inches, if this thing can extend out 12 inches, then that would be the maximum this guy could move would be what? 12 inches. So the length that that rod can extend out, we refer to that as the stroke. The stroke of this cylinder. This is the term that we use in fluid power for hydraulic or pneumatics. So if I could come up with something that spins and we can indicate the direction, then we can eliminate the stroke problems. So a resolver does almost exactly the same thing. What it's doing is it's putting one sine wave in here is putting another sine wave in here. They're calling it a sine and a cosine. And then what they get out, the phase they get out would indicate, and the strength would indicate what? The amplitude would indicate the position, and the phase would indicate the direction. But this is not linear, this is rotary. That makes sense? Same principle. But this guy is called, the rotary one is called a resolver. But it works on exactly the same principle. And the linear one is called a linear voltage differential transformer. LVDT. Now, are these all the things, all the sensors that's going to sense position? Probably not. You know, we have ultrasonics that we can use. What's ultrasonic? Choose a high frequency, an ultra frequency pulse out, and then it finds how it hits something, reflects back, and we can calculate the distance with what? How long it takes to come back. Everybody watched the movie in the submarines while they ping them, right? That's exactly the same way. It's just high frequencies. High frequencies, air likes high frequencies. Air don't like really low frequencies. Water don't like water. Water don't like high frequencies, but they like real low frequencies. So that means sonar is probably extra low frequency pulse that it sends out. But when it hits something, it does what? Bounces back, and then they know the position. But the problem is, they don't use that often anymore. Because once you ping them, they what? If it's another submarine, they what? They know where you're at. So, both of them use different techniques. In fact, they can't transmit underwater because frequencies that would transmit are such high frequencies, right? Understand? So they do transmits underwater. They at extremely low frequencies, but the antenna they string out of the back of the submarine is like 2 miles long. When they string that thing out because it's such low frequencies, it goes such a long way from it. Because water don't like high frequencies. So normally when they communicate, they float an antenna. They pop a little antenna up out of the top and communicate high frequency. But yeah. So I will hook up an encoder and we'll look at it with an oscilloscope. Y'all not required to have an oscilloscope. Is a measuring piece of equipment. But what it does is it shows you what's there. A voltmeter averages everything out. So if you take a voltmeter and you stick it into that wall outlet and it says 120 volts, what's actually going on, guys, is oops. I'll get this in a minute. Now this might not be pretty, but it's hard to draw this thing. So outbound power generates these waveforms right here. And these all should be the same height and the same width. And we call this a sine wave. I think we talked a little bit about that, right? No, we call this voltage peak. So this would be voltage peak positive, and this would be voltage peak negative. And the measurement between here and there, what do you think we call that? Yeah, voltage peak. So we come over here and notice I get no work during this time. We have no volts. If we have no volts, we have no current. If we have no current, we get no power, right? Understand? And then it comes up vertical, and it, not quite vertical, and then it lays over, and it hits V peak, and it's at V peak for no time. And as soon as it hits V peak, what happens? Yeah, it starts dropping down, right? Then it hits zero. So the work we get out of this is an average value. So my meter, if it might measure 120 volts AC, but it takes about 370 volts to get 120 volts worth of work. An oscilloscope would show you that because the oscilloscope shows you what's there. Your meter's going to do what? Your meter averages everything out. So if I was looking at a pulse waveform, it would vary, the voltage would vary depending on the width of these pulses right here. And we'll look at that too later on. But my scope would show me the pulses. My meter would do what? Average it out. So that's the advantage of an oscilloscope over a meter. It actually shows you what's there. A meter can't see noise riding on top of your DC power supply. A scope could. Scope is an invaluable tool, but they're fairly expensive. Well, that's not true. You can get an analog scope, but they're big and they're heavy for around $250. A digital scope, which is small and light, would be about twice that. So a lot of these sensors, if you wanted to see the output of an encoder, you couldn't do that with a meter, right? You'd have to have a what? Oscilloscope. So this is going to be our first lab here. These are proximity sensors. So what do we mean by a proximity sensor? Proximity, what does that mean? Nobody even knows. Proximity. So we got position, now we're moving into proximity sensors. So this over time, proximity means next to proximity. Police say it all the time. That means they're in our proximity. It means they're close. The police use it. And this way means it's next to. So a proximity sensor technically does not sense position. It senses when the device or the object is at a certain spot.
Ready or not ready?
Know if it's there or not there. So if I was a position sensor, I would know that my hand is over here and I know it's over there. If I was a proximity sensor, basically I have, like the horses wear. And I would only know what? When it was in front of me. That's proximity. So a pot, we can use a pot to give us position. We can use an encoder to give us a position. We can use an LVTT to give us a position, but it's always within a certain range, right? You understand? Okay. Proximity only knows when it's at a certain spot.
So it's kind of like on the amateur line when you put the blocks in?
And a light comes on. You take them up, they go off. Yeah. Or when it moves down through there, it knows if a part is present or not present. It don't know how many parts are there. All it knows is a part is present. So proximity means it's going to check when something is at a precise location. Now the first guy that they came out with, let's bring this up. So we know what a sensor is, a device capable of responding to a physical stimulus. Right? A device that converts physical stimuli into a what? Electrical. And we got two types. We got analog and digital. We looked at that a little bit, right? So position. So what we're going to do over here in our list is we're looking at what? Proximity. Proximity sensors indicate if a device or an object is at a certain place. I need to change that from device to object. We'll do that right now. Limit switches, magnetic reed switches, optical proximity switches, holophonic sensors, passive and inductive sensors. These are the proximity switch sensors that we're going to look at. Now the first guy that came out was a limit switch, and that was technically what it was used at the time to see if a machine had reached its limits. Now, technically, a limit switch is a proximity switch, but this computer right here loads its operating system off a disk. A lot of our, in fact, a lot of our newer computers is going to what they call solid state disk drives. So the operating system that makes this computer right here operate is not in the computer. It's loaded every time. Now, what advantage does it have to load an operating system off this? It means we can upgrade it, we can change it, right? If it's built into the machine, we can't do that. So this is a proximity switch. The original operating system was called a disk operating system, which most people call DOS. You ever heard of DOS? Yeah. Well, every operating system after that, DOS was a text-based operating system. You had a command line. You had to learn all these commands. You had to type them in. You had to learn all the syntax for the commands. So there's a lot of way to go wrong. Eventually, they came out with operating systems that used the graphical user interface, and we point and click with mice. But they are still disk operating systems. But what they did is we know DOS is the text-based operating system, and all the other operating systems they have names. Understand what we're saying? So all of them are disk-based operating systems, but DOS got the honor of being called DOS. So a limit switch is a proximity sensor, but it's known as a what? A limit switch. And so what we're going to do or look at is that these proximity switches fall into two categories. They're either going to be a contact sensor or a non-contact sensor. So what would a contact sensor mean? It has to physically make contact with the object that it's trying to sense is at a certain position. And then we have what we call a non-contact sensor. What does that mean? Non-contact reach. It senses it without touching it, right? You understand? So what is over time is that solid state proximity sensors, they're going to be, or these guys are now called proximity sensors. So if we say a proximity sensor, it means it's a non-contact sensor. And then we have a limit switch, which is a contact sensor. That makes sense? So switches and push buttons, we know about these guys. These are definitely proximity sensors. We don't think about them, but what do they detect? When your finger is at a certain spot, right? That makes sense? So, of course, we have push buttons. We have momentary contact switch buttons. All types of ways. We have what we call selector switches. We don't use very many toggle switches in the industry. Because what they're trying to do is come up with a standard way that people that work in the industry have to operate these. And a lot of times people in the industry has to wear gloves, right? You understand? So they want them to be able to operate without taking the gloves off and getting this little tiny toggle switch. Then we have limit switches. Limit switches are electrical mechanical devices that make physical contact with the object. We have what we call an operator. An operator is what we hook to the limit switch that actually the object strikes. So here the object literally has to strike this limit switch, this limit switch. The guy that does the striking, we call that an operator. We're going to have two types we'll talk about: pilot duty. These are pilot duty are basically designed to run loads. Then we have electronic duty. These guys are basically used to input to programmable controllers. They're not designed to run loads. They just provide input. Are we okay? Yes, no? I know these slides are up on the site. Huh?
while we're waiting, I have a question. Kind of sense to look at South Wildland and to start the school with Warren. Yeah, it's essentially ago. I mean, you perfect. Keep your hands out of the work.
That was a good thing.
But it wasn't like pushing, you know, it was just like a little finger through.
Well, it was probably like a capacitor sensor. Kind of like a lot of your TVs turn on now, you don't have actually a button. You've got a little groove you put it in. Probably a capacitor sensor. Which is in this section, by the way. So these are limit switches. So normally the limit switches, these are going to be a rotary type or a plunger type. Some of them you can change out by changing the head. You see the screws up there. You can take this out and put a plunger type. And then we have all these different types of operators. We have whip, we have rollers, right? That makes sense. This is a pilot duty. These guys are designed to run loads. I've seen these guys run motors before. So the contacts on these are pretty heavy duty. In fact, that's what we have over here. I think the one we have here would be considered a pilot. Some of them have a limited stroke, by the way, how far they can actually move. This happens a lot of times. People won't come back and mount them correctly, and whatever strikes them pushes the arm over too far. And if it does, something's got to break, right? I've seen people doing arm wrestling. Y'all seen that? Everybody saw arm wrestling championships. And I've literally seen arms break. So like I said, we got all types of operators. These guys are, now what's wrong with limit switches? What's some of the problems you think with limit switches? Electromechanical, exactly right. So these are electromechanical devices, which means what? Get fell in two ways. These guys have to make physical contact. Anytime we rub against something, we wear off a little bit, so the operators eventually are going to wear off too, right? Understand? So these guys are going to have to be maintained. These are electronic duty limit switches. So if we went over on the Amatro line the other night, you probably saw, I pointed out some limit switches. These are little tiny things. These are not designed to run big loads. They might run a light, but that would be about it. Most of the time, these guys are used to input into some type of controller, like a dedicated controller or a programmable logic. So these guys are not designed to run a load, right? You understand that? Any questions?
The light duty is not designed to run a load.
Yeah. Heavy loads. We can't say, because it's a switch. Somebody out there is going to run something off of it, right? You understand? They're not designed to run a heavy load. They can run light loads, but not heavy loads. So technically, the input of a PLC is a load. But yeah, but it's only like, I think 40 milliamps is what most PLCs pull. So that's not much at all, right? Reed switches. Dang, guys, I didn't bring my reed switch over here. Gosh, darn it. Okay. Well, let me see if I got one. Oh, yeah. This one? This one right here is not? Okay. I need to upload a new version. I can't see. So we have two types of reed switches. This one on your left is the one most often we run into. The one on the right was very, very popular for a while until they realized that mercury is dangerous. Yeah, the symbol, this is, mine's don't look real good. But in motor controls, this is the only symbol we get. It's going to be a diamond shape. In PLCs, all your sensors are going to be inside a square. And then it's going to have a diamond shape in here. 2 lines. And it's going to give you an indication of what the sensor is. So if it's got this trough, that means it's a magnetic sensor. It senses a magnetic field. So it's not, I don't want to put it's a magnetic sensor because technically it's not. It senses a lot. And then what we'll do is we'll come below that and put one normally open contact. And then up here, this would be 1. So this is going to go toward L1. And for this sensor, this is going to be 3. And this is going to go toward the load. But that's just for this sensor. We'll have to look at some solid state sensors. This is going to go on DC, this would be plus and this would be minus. Yeah, what we have to understand is that when we get into solid state, what we call a solid state sensor, what do we mean by that? This means this guy's going to be electronics. That's a term, another term a lot of people use for electronic. So that means this guy's going to have electronic component. A solid state sensor does not have a contact. It uses a solid state device to simulate a contact. That solid state device cannot drop 0 volts. It's a semiconductor. So a solid state sensor will drop a voltage across what we call the contacts. That makes sense. It's not mechanical, it's electronic. And a solid state device can never drop 0 volts because it's a semiconductor. If you see a solid state device drop 0 volts, you might have taken the thing out and throw it away because it's short. I should say it will never drop 0 volts if it's not bad. And that's the way we can determine if the solid state device is shorted. If it drops 0 volts across those simulated contacts, then we know it's bad, right? So when I see this symbol, guys, I don't know if it's solid state or if I don't know it's a mechanical. We'll be able to tell a Hall effect because a Hall effect doesn't have to be powered up. Not a Hall effect, excuse me. A reed switch, it does not have to be powered up. It only has 2 wires. But it will have the same sensors. So the solid state sensor that we'll talk about, it has exactly the same symbol. It's going to have the trough there. It's going to have the switch there. But it's going to have 3 wires going up. And I know right off the bat this is a solid state because this guy's going to have to be powered up. This guy's going to connect to L1. This guy's going to connect to L2. This guy points toward the what? The load. This guy connects to L2. This guy points toward the load. So that would be the output of a solid state. So if I see a 3-wire sensor, I know it's got to be solid state. 3 or 4 wire. And we'll look at the colors here in a minute. Unfortunately, on some of the stuff that we've got mounted, they don't let you see the color codes, but we need to learn the color codes in this class, right? Because that's the way you would hook them up. So photoelectric sensors. So we mean photoelectric means these guys are going to do what? They're going to detect things by light. And this is our first lab is on the first proximity sensor we're going to use is photoelectric. So probably no, I'm sorry, we're going to use an inductive too. So these are photoelectric sensors. One form. And you see how this guy works? So we have a what? Light source. Over there we got some type of photo detector. And these look like batteries. So what's going to happen is as the batteries are going to really break the beam. So when the beam is broke, we know something's there. When the beam is not broke, we know something's not there, right? That makes sense. So this is one type. Guess what we call this type? Somebody said 0208 already does it. Through the beam. So the object we're going to detect passes what? Through the beam. So these are through the beam. Some people call them direct scan. I just saw that before. Most times it's through the beam. If you type in direct scan on the internet or through the beam, you'll probably get some of the same. By the way, you normally can't see light. It's like on TV when they show the laser beam. You know, you can't see light when it's passing through the air because there's nothing to reflect off of. Unless they put what? They put smoke up sometimes. No, you can't look at it.
I have a friend called, and I mean, it might be something in the air, just floating in the air.
Yeah, if he's vaping or something in there, right?
I mean, but it's like we shoot it from the building, like I can shoot to the next building, and I can see, not the whole thing, you have to see the majority of it, like, bang.
When it's hitting something.
Yeah.
But on TV, where they show them like they're dang strings, right? So this is just showing the beam. So what we have here is we have 2 units. We have a transmitter and we have a detector. And something moves through it. So this sensor right here would give me back a true when there was nothing there. Because this breaks the beam, right? You understand? So if we were going to do this in a motor control circuit, we'd have to come up with a way we'd want to do. So we might have this control a control relay, right, and use the normally closed on the control relay. So when the device came through, the control relay would drop out and the light would come on. Then we have what we call a retroreflective. Oh no, they showed the code. So through the beam, what's some problems we're going to have with the through the beam? Yeah, so the alignment of this is pretty critical, right? We have to make sure these are aligned. you don't tighten them down or something, this could cause you a problem, right? Or if they get hit, they might do what? They might misalign. So these guys have to be aligned pretty good, right? But they have these have the longest sensing range because the beam is only making one path across, right? Understand? The next time the guy we have is what we call a retroreflector. So y'all seen retroreflectors before. In fact, that's a good picture of it right there. These are the ones that we have. So this is one of the labs we're going to do. We're going to use this photoelectric sensor. And this is a retroreflector. So a retroreflector, we run into we can do it with little triangles or we can do it with glass beads. But we run into retroreflectors all the time. Like a lot of people, when they're riding their bicycle at night, they'll have a retroreflective vest. And what that does is it tries to reflect back to the source. So if it was a mirror and your light hit it, it would bounce that way. But a retroreflective, even though I'm over here and the bicyclist is over here, it reflects back to me, right? You understand that? Or the things in the roads are retroreflectors too. They do that now on a lot of highways because a lot of times when it's raining real hard, those white lines disappear, but the reflectors don't. Stop signs and stuff like that, the letters are painted with retroreflective beads. So when we're over here, we can still see stop signs. So what's nice about a retroreflector is my alignment doesn't have to be perfect, right? You understand that? So here's the actual optical sensor that we're going to use. We can use this as either a diffuse sensor or retroreflective. And we'll see the difference in the range right off the bat. And I look at the colors. Can y'all see the colors?
Red and black and blue?
No, brown, black and blue. Brown goes toward L1. Blue goes toward L2, and black goes toward the load. So that gives us problems because we think of black being common, right? You understand that? So black is the signal wire. Brown's going to go toward what? L1, and blue goes toward L2. If this was a DC sensor, brown would connect to the plus. I shouldn't say toward. This is a solid state sensor. It's got to be powered up. So on this one, the brown will connect to L1. The blue will connect to L2. And black is going to connect to your wrong load. Everybody understand that? Yes or no?
Did blue go to L2?
Yeah, blue goes to L2. No, in DC, on AC, brown goes to L1, blue goes toward L2, and then black goes to the load. In AC. DC, brown goes toward the plus, brown connects to the plus, blue connects to the minus, and then the black goes toward the load. Y'all understand that? Let's draw it with our symbol. So here's L1. Here's L2. I'm going to come over here. I'm going to draw the symbol for my sensor. Oh. This is what? Brown. This is blue. This is black. If this is DC, this would be plus, and that would be minus. That's supposed to be 2 digits. So this is the way we'll wire ours. We're using AC, right? So black is what they call the signal wire. But if this was DC, so technically technically in AC, you could swap the brown and the blue wire, you'd have no problem, but you don't want to do it one way in AC and then another way in DC, right? You understand? That makes sense. So, here's the retro reflector. And you can just show the sensor too. But a retroreflective works similar to a through the beam. But here what we're doing is we're shooting the beam back. If it reflects back, it means there's nothing there. The object breaks the beam between the transmitter receiver and the retroreflector. So when the output of this sensor is true, so when that black wire has 120 volts on it, it means there's nothing there. Right? That makes sense? So this is where it depends on what you're doing. Now this guy I had a range, if these two guys had a range of 6 feet, that means these guys right here could be 6 feet apart. This guy right here could only be 3 feet apart. Because why? Because it's got to go back, hit the reflector, then come back this way, and 3 plus 3 is 6, right? You understand? So the retroreflector has a less sensing range than the through the beam for the same intensity light. That makes sense? So why is my shirt blue? Why is Kareem's green? Why is Maurice who's asleep? Why is his white? And why is Austin and Jackson's? He's got black and white. So what's going on there? What are we looking at? Or what light are you seeing? You're not seeing the light my shirt's absorbing. You're seeing the light my shirt is reflecting. So whatever this material is, when that white light hits my shirt, which has all the colors in there, it's reflecting back a color that you see. Right? Understand? Yes or no? Huh? It's not. It's a material. We see blue, and it's amazing that, how our body works, guys. That we can only see 3 colors, and then we have cones and rods right in our eyes. I keep getting confused, but the cones can see red, green, and blue. That's all they can see. And then we have another one, I think is the rods that can only detect shades of gray. And then we can take those 3 colors and produce light. But all we see is what's reflected off the object. So the light hits my shirt, everything but blue is being absorbed by the shirt, right? You understand that? And it reflects what? Blue, and that's what we see. So this is the way a diffuse sensor works. A diffuse sensor sends a beam out. It literally reflects off the object it's trying to detect. So a diffuse sensor. So the difference between a retroreflective and a diffused is a retroreflective depends on a light coming back from a reflector, right? You understand? Where a diffuse sensor actually senses the light reflected off the object. So what's the problem with these guys? What would be the limitations of a diffuse sensor? So the amount of color, so different colors reflect further than other colors. Right? You understand that? So black does not do what? It does not reflect. Of course, there's no such thing as perfect black, right? Except those guys that got trapped in that cave in the Philippines, that was probably perfect black. You ever been up to what's the falls up in Chattanooga? Ruby Falls. You've been down in there when they in that cave when they turn off the lights. You'll see what black is, guys. That is dark. But see, even Jackson's his is not perfect black, right? So these guys can detect black, but they got to be what? Really close to it. And then, of course, depends on the color of lights. All our diffuse sensor over on the lines, they all use a red light. So that means if they see red, it reflects what? Really well. And of course, if they see chrome, it reflects even well. Green, it wouldn't reflect as green wouldn't reflect as much. So that means the object would have to be close. So these guys have a very limited range. This guy right here is as far as range goes, these are the worst. But we can do things like that. It's really neat. Most of these sensors have an adjustment on it. All right, some of them have a. This looks like it's got that. Some of these sensors you can actually train them. You can actually train them to see a color and do what? Ignore all the rest of it. Well, we had one up in when we went to the NC3, they had one that had a training button on it. So you could put the color you wanted it to see, put it in front of it, and you could test it. And then from then on, if you put any other color in front of it, it wouldn't see it. The sensors we have over in our line, they have a little screw adjustment on the back of it where you can set what you call the selectivity or the sensitivity. So some of them over there, guys, are adjusted so they don't see black. And if you ever watch on the Festo line, if you ever watch it put the cylinders together, the red ones and the chrome ones are assembled the same way. The black one is assembled different. So when it figures out what rod it wants to put in there, you'll see the robot come down and look at the cylinder, and it's adjusted not to see what, not to see black. So we can train these guys to see specific colors. Some of them. And that's probably what these buttons on the top are for. Like I said, I got the part number on this one. I could probably look it up. But some of them, you can actually train these to see different colors. So these are photoelectrics, by the way. By the way, the sensor that you got in your hand, we can run that diffuse sensor and a retroreflective is about the same. So over there, when you do your lab, you'll notice that when you got that retroreflector on there, you can go back like 8 feet and still break the beam. But when you take that retroreflector off there and you use it as a diffuse sensor, you're going to have to get within like 6 inches before it triggers. Then we got this guy. This is called a definite reflective. And this is just a different variation of a diffuse reflective. Now, why I bring this up? Because most of y'all use this all the time. What do you think that is right there? What type of sensor is that? Photoelectric sensor. What type of photoelectric sensor do you think it is? Well, I don't have a retroreflector on my surface right here. I've got a surface right here, right? It's a diffused, right? So it's bouncing the light off this thing, hits this table. Right. But can y'all see it? I'm gonna pick this thing up just a hair. It don't work anymore. Yeah, well, that's just.
So with the diffuse sensor, not long to detect color?
What's that?
The diffuse sensor to detect color?
It does, but it gets a different reflection depending on the color. and it depends on what color beam do they use. Red is very popular. In fact, every optic photoelectric sensor we have on both the Festo line and the Amatro line uses red. That means it'll see colors toward the red spectrum really well. Colors toward the dark spectrum, black spectrum, it starts not seeing so well, right? But we can play around with the sensitivity. What a definite reflective does is that it's got a beam that shoot off. This is exactly what's in this mouse. You can actually see this. If I got another mouse in my bag, I'll pass it around. I think I might have left it out. Yeah. That's like passing batons at a relay race, right? So a definite reflective is looking for the light to be reflected at a wad at a certain distance, right? Does that make sense? So here, this would be what? Too near. This right here would be too far, and then this right here would be just right. So you can actually see this unit inside that. You can see the beam shooting straight down, and then on the side you see an angle, a lens angle. And we see these things in all types of applications. It's very popular, by the way, on our lines to actually connect to the photodetector through the actual sensor itself through fiber optic cable. And it's usually plastic. Plastic fiber optic is a lot easier to deal with than glass. But it doesn't, it's got more attenuation. You know what attenuation is? Got over distance. So you couldn't run these as far as we could glass fiber, but they work really well in the industry because most of the sensors and what it does, it gives us the ability to put the actual sensing element outside of harm's way. So that way we might break a fiber cable, but we can replace that and it'll be a lot cheaper than trying to replace the sensor. So all our fiber over on the lines use the actual sensing element is off away. Except for some of the retroreflectives, for the diffuse sensor and the through the beam, they all transmit back to the actual sensing head through the fiber cable. And then we have these guys. These guys are called optical interrupters. This is nothing but a through the beam, a variation of a through the beam optical sensor. But what it is your transmitter and your receiver are set. The distance between the transmitter and the receiver is fixed. And when it detects it, it has to move between that slot between the two sides. We see these used a lot. Very simple. Now this is the actual makeup, but we don't really need to know that. This is what's called a phototransistor. It basically cuts on when it sees the light and it cuts off. So if you picture that sucker as a switch, when it sees the light, it closes the switch. When it don't see the light, the switch opens. So if it does see the light, this goes to 0 volts, and that resistor right there drops to 5 volts. And then when the light breaks, this guy here cuts off. There's no current flow here, so if there's no current flow, that resistor drops no voltage. Well, there is some current flow, even to a PLC, guys. The PLC, you're looking in the milliamp range, right? You understand that. So it's not going to drop. This guy's called an optical interrupter. Of course, the resistor is usually external. So this is an optical interrupter. So you should see Oh, it's on the top. One of them's got E on it, that's the emitter. One of them's got D on the top of it, that's the detector. Whatever we sense has to go through this blade right here. So these guys are replacing a lot of limit switches into a programmable controller. And what we'll do is we'll have a blade on the device that we're going to do, and it slides in between here. Optical interrupter. Oh, this is my encoder wheel that I was looking at. This would be an incremental encoder. I forgot I had this in my box. So what we do is we use a through the beam, right? We understand now. And through the beam would shoot through this hole, right? And so with this thing was spinning, it would go true, false, true, false, true, false, true, false, true, false, right? Does that make sense? And then we could use that to sense position, right? So what's nice about this, not only can we sense position, we can also sense speed with these things, because the rate of the pulses would give us the speed, and then the pulses would tell us the position. But there's nothing on here that says what position it is, right? You understand that? So what we would do with this is whatever's in motion, we would move it to a spot that we're going to set as the origin. And from then on, these pulses right here would mean something. That makes sense? Anybody want to hold that? Spin it like a top? I don't know if it's spin like that. No, too heavy. No, it won't spin. You guys take a break.